Active optics is an optic that responds to electrical stimuli that changes property of light. So for example, it could steer a beam, it could change the wavefront of the beam, distort the beam, it could modulate the beam, all in response to an electrical stimuli. My name is Malcolm Humphrey. I'm the Vice President and CTO here at PLX Incorporated. Most is monolithic optical structure technology. This is a MOST interferometer. So in this case, this particular application, we have a combination of beam splitters and mirrors that are used to combine two different beam paths into one and create interference fringes. This particular one is called a Michelson monolithic interferometer, and this is used for detecting vibration or distance or gas content. Essentially, monolithic technology is any optical subsystem that is captured within a glass structure, such as this one. So this is entirely one material, all glass, all the optics, all the structure, entirely one material, which means that this is very stable over time, temperature, shock and vibration. So the monolithic optical structure technology really enables the active optics technology in terms of delivering the accuracy and stability that you need for an industrial metrology system or a long-range laser tracking system. We use it to align all the optics, including the detectors and the beam steering device and the laser source, into a single monolithic structure. And what this means is, from the day we calibrate it to the day it's used at the customer, from all the temperature variations, shock and vibration that it sees, the accuracy doesn't change. It does not need calibrating from that point forward. The monolithic structure technology we use in both the tracking laser rangefinder and the O-LAMM. The O-LAMM is an orthogonal laser metrology device. Essentially, this is a device that scans a laser fan in a volume. So it's continuously scanning. Whenever it encounters a retroreflector, the retroreflector reflects a pulse of light back to the device. The device can then determine the angle of that reflector in both the X and Y plane. If you combine multiple reflectors together in a constellation, you can now track full 6 degrees of freedom, so position and pose. So what this enables us to do, for example, is track the position of a robot end effector as it's moving around a car body or perhaps in a machine tool. Allows us to track those devices with a very high degree of accuracy. So the O-LAMM is a scalable device. You can have many O-LAMMs in a network. So you can use the O-LAMM in industrial metrology applications, so factories, Industry 4.0, that's going to be the main uses of it, but we also see markets in interventional medical devices, so robotic surgery, radiotherapy, for example, we see applications there. So the TLRF is a tracking laser rangefinder. Essentially, this is a laser rangefinder where we are able to steer the outgoing beam and the receive part of the optic through a beam steering device. And what that allows us to do is, instead of ranging a single point, we can range multiple points within a electro-optic platform's field of view. We can also use it for tracking objects. So if we are able to steer the laser so it always hits the target, we're able to continuously generate bearing and range information on that target. So this is what we've proven with our concept demonstration, where we were able to track a drone at several hundred meters. We're able to generate the range and angle information with a very high degree of accuracy. A conventional laser rangefinder you may install on an electro-optic platform. The platform steers that laser, so essentially you can't move that laser rangefinder any faster than the platform it's on. So this platform is generally a pan and tilt system. They have a few hertz of mechanical bandwidth, so they don't move that quickly. The TLRF has over 1,000 hertz of mechanical bandwidth, so it can step between points in milliseconds. If you're looking to track and range a swarm of drones, for example, the TLRF can step and range and get position of each individual drone within that swarm. And for countermeasure applications, where you want to use, say, a ballistic countermeasure, that bearing and range information is important to be able to target your weapon. Same for directed energy applications. You need very good bearing, range and real-time data in order to hit those targets.